Thank you for your introduction. So the motivation behind our work is centered around program analysis in IDEs. Essentially what you see here on the slide is that an engineer interacts with a small code snippet. This is being edited. And what we'd like to do is that there is a series of program analysis running on this subject program. So for example, an uninitialized read analysis that reasons about which variables haven't been initialized before. And then we want to use this analysis result to put error markers on offending code parts in the IDE, because this way we give feedback to the engineer, like what are the potential sources of problems. If we would dereference an uninitialized variable, then there would be immediately a null pointer exception here. Now, interesting or importantly, the feedback to the software engineer should be very fast, let's say at most 1 second, because otherwise the development workflow is interrupted. So this is actually the problem that we would like to solve in our work. If we dig a little bit deeper, like how actually the technicalities for this workflow, and what we see here typically is that given the subject program, the IDE typically constructs the abstract syntax tree for that program. Then that gets transformed into some intermediate representation. This could be, for example, the control flow graph or the data flow graph. Essentially, the idea is that we want to abstract away from details in the AST that is not relevant for the program analysis. And here we encode, for example, context switches, reads and writes, all of the necessary information that the program analysis then uses. Then here we have this arrow, which essentially means that this representation will be the input to the program analysis. And then we have the different kinds of program analysis running, providing the useful feedback. And now, when the code gets changed, problem is that the interactive editing requires incremental maintenance. Essentially, in our solution, we would like to run the analysis incrementally. Instead of rerunning the analysis from scratch again and again, we want to consider what has changed in the program and then update the analysis result efficiently based on that change. Now, in prior work, we have already managed to solve or tackle some of these components in this workflow. So for example, we built a static analysis framework called IncA, where we could already incrementalize the construction of the control flow graph, for example, and we could already encode different kinds of program analysis. I will go into details like what is actually the category of the program analysis that we could encode, but the problem was that we could not encode all of the different kinds of program analysis that we use in custom lattices. And so this is the topic of the current work. So going into a little bit more details, we could already encode program analysis that rely on the powerset lattice. There are many different analyses that fall into this category. So for example, common expression elimination, versions of points to analysis, liveness, uninitialized read. These can all be encoded as using relations. Essentially, we are relating program elements to each other. And using the IncA framework, we could already incrementalize these analyses. But then the problem is that there is another category of program analysis that are using custom lattices. So for example, when we want to reason about numeric values, then we want to use intervals. When we want to reason about string values, like the common prefixes or suffixes, we want to encode string patterns. Then, for example, type checkers use lattices to encode types, how the types look like. And so the common for these analyses is that they use relations on one hand, so that is good, but then they also want to use custom lattices, generate lattice values, and then aggregate lattice values. And aggregation is important because typically when we have cyclic control flow in the program, then at merge points we want to aggregate lattice values together. You will see example for this later in this presentation. Now the problem is that prior work could not incrementalize these analyses, and this is the topic of the current work. So I would like to show you a concrete example. I'm going to use the interval analysis. Essentially, you see here a code snippet which has a loop inside. So we want to reason about what are the potential value ranges for the variables. So we would like to ask questions, what is the value range for the variable y at the loop head, for example? So a typical evaluation goes like this. So we start at the first statement. We are abstractly interpreting the effects of these assignments in the interval domain. This means that we assign the 7, 7 interval to x and the 0, 0 interval to y. Then from here, this gets propagated. And then also we do one round in the while loop, so we get these intervals. You can see here, for example, at this point we have now for the x variable 11, 11. This is actually coming from here, so from statement 4. And then because of the ternary expression, we also have a new interval for the variable y. Now, what happens here when we propagate back the interval from the statement 5 to the loop head, this is where aggregation takes place. Essentially, you can see here with the highlighted cells, like what gets aggregated together. So on one hand, for the variable x, we aggregate the 7, 7 and the 11, 11. We're using the least upper bound operator of the interval lattice to do that, and this yields us the 7, 11 interval. Then we take the 0, 0 for y and the 0, 1 from here, and this yields 0, 1 as the interval, the new interval. Now this gets propagated into the loop body, and then we do a series of iterations. Essentially, at some point, we will also use a widening operator because we want to accelerate the fixed point computation. For this example, let's just say that my widening operator is super simple. It will just say that the upper bound is plus infinity, just for this example. Now, when we talk about an incremental program analysis, what you have seen here, this was the initial computation, right? Because the incremental analysis wants to reuse the previous computation, the analysis result, and then update it efficiently. But we didn't have anything, so we need to come up with the first result, and this is what you have seen here. Essentially, for an incremental analysis, it is important how the values in this table depend on each other. So what you see here now, the table focuses only on the y variable. We started with this interval here, 0, 0, in the first cell. And you can see here through the iterations and through the aggregations how we got to the final values that are here. And these data dependencies will be important because when something gets changed in the program, we will use these dependencies to reason about what needs to be updated. Now, when we talk about an incremental static analysis, we can formulate two requirements. First of all, we want to have correctness. So it's kind of like an obvious requirement, but like saying it out loud, what this means is we want an incremental analysis to compute the exact same result as a from-scratch recomputation. Then also we want performance, so the incremental analysis should be significantly faster than its non-incremental counterpart. After all, this is the whole reason why we are doing this. Now going back here, let's do a program change. So essentially at the statement 1, I'm replacing the initial value of y from 0 to -1. And then in response to that, I would like to update the analysis result. So this means that at this cell here, we are deleting the value and then inserting a new value. Essentially, the replacement is encoded as a deletion-insertion pair. Now, a standard strategy to deal with this kind of change is to delete first and then insert later. So what this means, we delete this value here in the first cell, highlighted with red, and then we realize that according to the data dependencies, essentially we need to clear out the whole table. So because essentially every value depended on that through the series of iterations. Then based on the inserted value that gets inserted to this first cell, then we can recompute the new result, essentially the same story as before through the several iterations, and you can see here the updated analysis result. Now, this doesn't seem really good because we deleted too much and then redid the whole thing again, but actually at least the variable x was unaffected, so we kept the analysis result for that. Now, to be honest, in our solution, we are not actually keeping track of a whole table. What we are doing, we keep track of one column, and when aggregation happens, we simply want to replace the value. So we are only keeping track of here one column. What happens now when we perform the aggregation? This is the new aggregate result, and we want to replace this value in the cell with this new value. So what this means, we want to delete the old aggregate result. This is the -1, -1, and then insert the new value. This is the -1, 0. Now, according to our strategy, we need to delete first and insert later. So what we do, we start propagating the deletion, right? Step by step, we are invalidating the values in the cells. Here we are also, again, we need to consider the ternary expression. So then we also invalidate this value here in this cell. And then from here, the deletion gets propagated back, right? We had here a value that we wanted to insert, but now actually that value got invalidated, right? So there is a problem here. The analysis is not making a progress. So because of this standard strategy that we wanted to do, we had a deletion and an insertion, but then during the deletion, we actually invalidated the inserted value. And so we are back to an initial state where we actually had this value in the first cell, and then from there, we wanted to propagate it further. So let's go back for a moment to the aggregation. So once the aggregation happened, we had here a deletion and then an insertion. Let's take a closer look at these values. So what we did, we had the old cell value. We wanted to delete a value from there, and then we wanted to insert something. So we deleted old and inserted new. This resulted in a problem, so that's not good. But actually, if we look at these values, -1, -1, and -1, 0, what happens is that we are deleting a lattice value, and then we are immediately inserting a value that contains that value. So, okay, this means that actually it would be okay to simply insert new. So that seems good. Actually, we can even generalize this problem. So if old is actually less or equal than new, according to the partial order of the lattice, then we can do this. This is good for us. We call this deletion insertion pair an increasing replacement, if this here holds. And this is actually crucial for our solution. So what we do is, due to the monotonic aggregation, we will actually always have increasing replacements, right? We are using the least upper bound or greatest lower bound of the lattice, and because of that, because those are monotonic operations, we will have increasing replacements during the aggregation. So this is key to our solution, because then this way we can actually make sure that the analysis progresses towards a fixed point. Now, so this is actually our strategy. So our strategy will exploit the increasing replacements. So let's take a closer look at how this algorithm works under the hood, like in a high-level manner. So what happened is that in a standard strategy, we were progressing the changes immediately, eagerly, deletion and insertion. So whenever an insertion came, we essentially just simply handled the deletion first, and then whenever an insertion came, we also later we handled that insertion. But then when an insertion and a deletion came together, we separated them. We gave priority to the deletion, we handled that first, and then we handled the insertion. Now, in our strategy, that's different. We are using a buffer. So the thing is that as updates are coming in, we want to buffer them, because we want to take a good look at them, because then what we really want to do, according to the increasing replacements, we want to separate them. So we send some of the deletions here to the top, but then other deletions that actually can be paired with an insertion, they can go down here to the bottom. And so now what happens, we handle the deletions first. So those are the bad deletions that cannot be paired with an insertion. And then in the second phase, we handle the insertions plus the increasing replacements. So this is a lot of technical details. And this is typically what analysis developers do not want to care about. So there's a lot more to this algorithm. In our paper, we actually explain the full algorithm description. Also, I didn't talk about how the buffering actually works. Like when do we need to delay the propagation of the updates? I'm not going to talk about that. This is left for the paper. We also have a correctness proof in the paper, which is proving that the non-incremental version actually computes the same result as the incremental algorithm. So again, this is a lot of technical details. In our solution, we actually came up with a DSL that shields the analysis developer from all of these incrementalization details. We actually provide two parts in this DSL. The first part can be used to define your lattice definition with pattern matching, and there's a DSL for this. And then in the second part, you can rely on familiar constructs like functions, input and output parameters, for each, and iteration and pattern matching to encode your analysis implementation. Then we actually took this DSL and we implemented a static analysis framework around it, which we call IncA, and this is available open source. So I would like to say a few words about the evaluation. We used IncA and we asked the following two research questions. Is an IncA analysis significantly faster than its non-incremental run? The same corresponding non-incremental run. And is an IncA analysis fast enough to provide real-time feedback in IDs? Ultimately, this is what we want to achieve. We had two case studies. We implemented a strong update points to analysis using IncA, and we also implemented string analysis with IncA. These are reasoning about the longest common prefix and suffix of string values, and also what are the characters that a string type variable may contain during the execution of the program. Our subject code bases were real-world Java projects in sizes up to 70,000 lines of code. So what you see on this slide is the evaluation result. We start with an initial run, right? This is where we need to come up with the analysis result for the first time. So here the y-axis, this is a logarithmic scale. And here you see the strong update points analysis and the string analysis. These are the 4 code bases. So we started with the Google Truth code base, that is the smallest, and the Berkeley DB is the largest. This is the 70,000 lines of code. So what you see is the initialization time here. So the initialization time takes from 6 seconds on the Google Truth up to a minute on the Berkeley DB. So this is the first time when you run the analysis. And then we have the incremental update times. So what happened here, we performed code changes, thousands of them, on the subject programs, manipulating expressions, deleting statements, updating methods. And so we measured how much time it takes to update the analysis result. And what you see here is that consistently they are in the ballpark of several milliseconds, which is exactly the kind of numbers that we're looking for when we are targeting applications in IDEs. Now, at this point, I would like to mention that the analysis that the results are presented here, this is for an intra-procedural analysis. It does not analyze across function calls. We are actually currently working on inter-procedural points analysis in IncA, and also type checkers for Rust, for example, and we already see promising incremental performance. So in summary, I explained to you that our work is centered around program analysis in IDEs. The current state of the art wasn't expressive enough to encode program analysis that use custom lattices. I also showed why it is difficult to incrementalize such kind of analysis, and our solution relies on increasing replacements. So this is key to our solution. We built a DSL to shield the analysis developers from all of the technical details and the whole analysis framework around this DSL. And finally, I showed some results about the evaluation. So if you want to give this a try, IncA is available as an open source software. I'm happy to take any question, and thank you for your attention.
We have time for a few questions.
Question? So how often do you raise a update interrupt to the IDE? Because the updates could happen in many. See, I could have removed the 0, but I have not inserted -1. Do you invoke, hey, there is a change, or do you change it after -1, or do you change it after I do -1, 2? So at when do you invoke these interrupts?
So for example, if you would have the value that I had there, like initially it was 0 or -1, and then you delete that value, that is a change that we immediately handle. So
yeah, but that's now empty. What do you do? See, I deleted. See, let's look at his keystrokes, right?
Yeah.
0, I put a backspace.
Yeah.
Right? So now,
so
at that point, you cannot run your analysis because you don't have a value.
Well, you can just invalidate the result for the variable y.
Right, and then if I do -1,
yeah,
you recompute.
Yeah.
And after that, if I put next to -1, if I put one more 2, it would again recompute. So the number of such updates could be a lot, isn't it?
Well, that's true, yes. I mean, but this is why we had this evaluation. So actually, it seems that we can handle that efficiently. And also, I think what is key here, or what may be a bit confusing, is that I was talking about increasing replacement, but increasing replacement do not actually happen from the user. Actually, happens very rarely. But in the system, when aggregation happens, that is what we always do by construction.
To perform your analysis, you need to store the entire intermediate stages of the computation, right?
Yeah.
Does that add a lot of overhead to the analysis tool, or is it negligible?
You mean the internal state, like caching the analysis result, or what do you exactly mean?
Yeah. So if you want to change the incremental change that you have in the entire, you store the table of stages that the static analysis is done, right? If you didn't want to do that, you wouldn't have to store any of that. So presumably that adds some overhead to the tool.
Well, I mean, the table, we do not want to store those tables. I mean, those can get really big. That's why I was talking about that we only keep track of one column, essentially. And that column, we want to stick to that. I mean, that is, after all, the analysis result that we want to reuse and update efficiently.
So you say that this increasing replacement is the main novelty of your technique. So what happens in the experimental results if you disable just that little feature and do not recognize incremental or this
so
increasing replacement?
without recognizing the increasing replacement, the analysis would not even terminate when you are using lattices and aggregate over lattices. So increasing replacements on one hand, it's good for performance, but on the other hand, it's key to actually ensuring that a fixed point can be reached.
Okay. One more question. So now that you showed the results for intra-procedural analysis, what happens if you, as baseline, just reanalyze the entire method?
Yeah, so
instead of the entire program?
yeah, actually, so we also had measurement results for this. What we can say is that still, like reanalyzing complete methods compared to the incremental version of that, we see like an order of magnitude speed up there.
So I actually have a quick question before we go to the next speaker. That goes back to the first question that you had. When do you trigger those incremental analyses? Do you wait until like the user is done with a few characters, or with every single keystroke?
Every single keystroke. It's like eagerly, immediately when the program gets changed.
Okay.
I mean, otherwise, I don't know what would be a good way. Like when you want to insert a breakpoint, now it's time to recompute. Like when you save the file, maybe, or.
I don't know. That was my question.
Yeah. So we are eagerly doing that.
Okay.
Sorry?
The IDE is already segmenting series of actions. When you hit undo, it's not just the last key.
Yeah, I just have a quick question on the same note, but sometimes when you may not have a valid AST even, so how does this work? Because I may really remove some parentheses or etc. You need to fix this somehow.
Yeah, so this is actually a technical detail. We are using the metaprogramming system under the hood. This is where we have the integration, and it uses a projection editor. So actually there is always a valid AST under the hood. And we have an integration with the static analysis framework in that IDE. But I can talk to you more about this because this is actually a longer story, like how this works.
Okay, but this doesn't seem like a detail to me because, but okay, I'll take it offline.
Yeah, I think if you have any more questions, we can take that offline after the session. Let's thank